Okay, children, once again, welcome back to the online tutor. So in this tutorial, I'm going to discuss about the friction lesson and some examples of the frictions, right? So the last tutorial set, I discussed about the straight lines, right? So I invite you to watch the straight line lessons, and also these days I'm working with the trigonometric A and B formulas, right? So you can watch it as well, right? Okay, then let's move to the definition of the friction, right? So the definition of the friction is when two surfaces slide against each other, a dissipative force called the friction act to resist their motion, right? So assume a object is located on a horizontal surface, right? And we are going to shift that object to the right hand side with the force P, right? And there is another force towards the other side, right? So the left hand side with F, right? So F is known as the friction force, right? So the friction force is always located as a resistant force, right? As a resistant force, dissipative force, right? So this is the definition of the friction, the law of friction, right? Okay, children, next we'll see what is the frictional, what is the graph of the friction, right? So here you can see the graph of friction, right? Always the horizontal axis is indicate the applied force, right? It's Wx, and the vertical bars indicate the friction, right? So what happens if you increase the value of the that applied force, right? So relatively the friction force also increases, right? So the friction force, but there is some special location, right? It known as Fm, the friction value. When the friction value is Fm, so the particle is trying to move in on that surface, right? So Fm is the last force that we have. So the last force mean it's known as static limiting frictional force, right? So it's Fm. So after, if you are increasing rapidly the W applied force, then what happen, the friction force will be little bit lower than the Fm value. Then the particle is trying to move on that horizontal or the surface, right? So that friction is known as a kinetic friction value. This kinetic friction value mean it is a dynamic friction value, right? So always the static limiting friction value is more than the kinetic friction value, right? So in our combined mathematics syllabus, we are always dealing with the static frictional forces, right? Not the dynamic friction forces, right? So actually this lesson is a static lesson, that's why. Right, so when a motion starts when Wk greater than Fm, after the frictional force remains at a constant value throughout this state less than the static limiting frictional force. This is the coefficient of friction, right? So what will be the coefficient of friction? The coefficient of friction means the limiting frictional force is divided by the normal reaction, right? The coefficient of friction is always a constant, right? It cannot be changed anyway. So once you apply the limiting frictional force value, right? So, limiting frictional force is always fixed value. That is the highest point reached by that our graph, right? So it's always fixed. And R also, the reaction between the surface and the object is always again fixed, right? So therefore the mu is always constant, right? The mu is known as coefficient of friction, right? So it's equal to the limiting frictional force divided by the normal reaction. Then we'll see what is the angle of friction, right? So the angle of friction, when two bodies are in contact with each other, then total reaction at the point of contact is the resultant of the normal reaction and the frictional force. At the limiting equilibrium, the angle lambda, which is resultant make with the normal reaction, is called the angle of the friction. So always, children, the angle of the friction is measured relative to the reaction axis, right? It's not to the Fm axis, it's always reaction axis. So Fm means our frictional force. No, this angle is measured only relative to the reaction axis, right? So you can see the tan lambda equal Fm over r, right? So I think you have remembered the coefficient of friction. It all was also Fm over r. No? Then the mu and the tan lambda will be getting equal, right? Then tan lambda equal mu. Therefore, we can equal this tan lambda and mu, and we can use it in our questions, right? So please remember what is the lambda value and the angle of friction mean the angle of the resultant, right? So the angle of the resultant which make with the reaction. So this is the angle of friction. Okay, children, so the next one, so this is about the frictional force. We have several type of frictional forces, right? So actually once you increases your force wk, right? So what will happen, the particle is not moving, right? But once again you increase it rapidly. So if the limiting frictional value and the other your applied force is once equal, then the object is try to move on the surface, right? It's trying to move, but actually it's not, right? But if you increases again, right? So the input force, then what will happen, the particle is trying to move, right? So it's moving. So here my left hand side diagram, which F1 mean my applied force, right? The F dash mean my frictional force, right? So what it's actually F1 is less than F dash. Here F dash is the limiting equilibrium. We always F dash is limiting equilibrium. So what I'm going to do, I'm dividing both side by R. Then F dash over R less than F dash over R mean mu, no? Then F1 over R less than mu, right? So then F1 less than mu R. So actually the angle theta is less than the lambda. So lambda mean the angle between the resultant and the reaction of the limiting equilibrium time, no? But the theta is that situation. So the F1 value frictional angle, right? So what happened to the second diagram? It's F1 equal to F dash. So what's that meaning? Your frictional force, the limiting frictional force and applied force both are same. Then I'm going to again divide by R. So F over R equal to mu. Then F equal mu R. So what happened? Theta and lambda both will be equal. Tan theta equal tan lambda. Then tan theta equal mu. Right? So here these two situations are called the equilibrium situations because the particle is not moving on that line. Right, so the particle is trying to only move when the F1, your input is more than the limiting equilibrium value. So the third diagram also discuss about that situation, right? So F1 is greater than F dash, then F over R is greater than mu. F greater than mu R, then theta greater than lambda, tan theta greater than tan lambda, tan theta greater than mu, right? So if you want to move in, if you want to avoid the equilibrium of the friction, right? If equilibrium of the system, right, against the friction, then you just need to apply some force more than friction. So then you can move to that object, right? So this is my short note about the situations, right? Always we are dealing with F less than mu R, right? You have to remember these equations, otherwise you can't do the inequality sums or something in the friction lessons, right? So please remember, be mindful about the F less than mu R. So that happen when the force, applied force, is always less than the limiting equilibrium force, right? And also the one more important thing is we are always dealing with the limiting equilibrium value, right? So limiting frictional value So actually, relative to the relative uh, limiting frictional force, so we can check our force is always less than this, then we are survive, not moving, right? So likewise we can deal with, we can make our conclusions with the friction lesson, right? So right, so this is at the end of the theory parts in the friction. Actually, this is small lesson, right, which is in grade 12 syllabus, right? And we'll see some questions. Okay, children, this is my first sum, right? A ladder of weight W, it is placed on the one end is touching a rough wall and the other end is in contact with the rough horizontal floor. Coefficient of friction at the floor and the wall are mu and mu dash respectively. Show that the incline of the ladder to the horizontal when it is just about to slip is tan inverse 1 minus mu dash over 2 mu. Right, the first of all you just need to draw the diagram. So the ladder of weight W is placed on the that one end is touching a rough wall and the other end is contact with the rough horizontal floor, right? The coefficient of frictions are different both for floor and the wall, right, which are respectively mu and mu dash, right? So the ladder is equilibrium, right? So we just need to find the angle of the ladder make with the horizontal, right? So we'll see how to find the value of the theta. Okay, this is my the wall and the floor, right? uh, and I'm going to place my right. So I assume this is R and this is S, and also the friction force is F dash 1. This is trying to down, and it's the friction was F2 dash, right? So this is the angle theta. I just need to calculate it. The weight is W, right? I assume that weight is W. So this is the diagram. Okay, the first thing is you just need to draw a diagram, right, including all forces, right? And the next thing is a simplification method, right? Right, so we'll see how to simplify this using these forces, right? So here this F dash can be written in mu R, no? Because friction equal to mu and R. And considering the horizontal forces, S equal mu R. So S equal mu R means F2 dash will be mu dash mu R, because the wall friction is mu dash. It's mu dash into S. So S mean mu R. Mu dash R. This is F2 dash. Then I'm going to take the horizontal force as well. Then it will be R plus mu dash R equal to W. Then you can take R out. 1 plus mu dash equal W. R equal W over 1 plus mu dash. This is my second equation, right? So we have now S and R both. Then, so two components are taken. The next step is taking a moment some instant. right? So I'm just going to take a moment around. You can take any position, A or B, right? I'm taking A to the anti-clockwise direction. So this value is A, right? And R into 2A cos theta, 2A cos theta, and mu R into 2A sin theta equal minus W into it's other way around, A sin A cos theta equals 0. All A's are cancelled. 2R cos theta equal mu R 2 mu R sin theta plus W cos theta. So we need to calculate tan theta now. Two R equal 2 mu R. I'm going to divide by cos theta W. Then actually W can be written in 2R 2 mu R tan theta. W can be written in R times 1 plus mu dash. Right? All R's are cancelled. Tan theta equal, you can substitute it. Okay, this is the answer of tan theta. Okay, children, so let's move to the second example. A uniform solid hemisphere rests with its curved surface touching rough horizontal plane and rough vertical wall. Coefficient of friction is mu. Show that the angle that the base of the hemisphere can make with the horizontal is sine inverse 8 mu into 1 plus mu over 3 into 1 plus mu square. Hence show that total reaction make distance 8 times 1 minus mu over 1 minus mu square plus square from the wall, right? So first of all we just need to find the angle, right? The thing is how to draw the diagram. This is actually solid hemispherical object, solid hemispherical object. So we don't know the location of the center of gravity of these kind of hemispherical, right? So later I will show you it is in our center of gravity lesson, but we can directly use it, right? So the thing is how to draw this. The solid hemisphere is raised with the curved surface touching rough horizontal plane and the rough vertical wall. The coefficient is mu, right? This is my wall and flow. This is my hemisphere, right? This is symmetric line, and these are my reactions, right? Surely the reaction should be passing through the origin, no? The angle is alpha. The reactions, these are reactions. These are reactions, right? R and S. It's perpendicular. Origin. Actually, you just need to know where the center of gravity located. So I assume here, right? So actually the mechanism is, I will show you. So center of gravity of the solid hemisphere radius A, it's located at 3a over 8 from the base. 3a over 8 from the base. Okay, so we just need to find the angle. This alpha, right? So here, this is my friction, mu r, and this is also my another friction, which is mu s. Horizontal forces I am taking, mu s, mu r equal to s, then s equal mu s, mu r. Then mu s will be mu squared r. The next step is we have to take a vertical forces. E squared r plus r equal to w. R can be taken out, then w over 1 plus mu squared. Okay, so I took x component, y component and one moment. This is the mechanism of doing sum. Two component and one moment. Okay, this is perpendicular. Take a moment, round off. Okay, this is moment, I am taking moment, right? I think you can do it. Okay, this is my answer of sine alpha, right? Hope you can do it now, right? And let's move to the next round number of this sum. Okay, the next is hence show that the final reaction that distance make distance a 1 minus mu over 1 plus mu squared from the wall, right? So the what is final reaction mean? These are my friction forces, right? So which are make a resultant, right? So all resultants are collinear, right? Otherwise it will not be equilibrium. So this is the collinear position, right? These my backlines are intersected each other, right? So that is the my intersect and collinear point, right? Actually these are angles, right? These are frictional angles. So I told you in the theory part, right? These are lambda. This is the collinear point and this is the final reaction position. So we just need to calculate the distance from the wall to that final reaction position. Here this is alpha and this is again alpha. And sine alpha will be, it was taken 1 mu 1 plus mu over 3 times 1 plus mu square. This was taken before. And this is the distance, actually the distance from the wall to the final reaction. So D can be written in A minus A sine alpha, no? 83A sine alpha. So D will be A minus. So you can calculate to find the D value. One getting cancelled. A mu taken out, mu minus 1. I'll repeat it again. The simplification.
Then we found x component, y component and one moment to reach the answer. So the last part, it was a minus a 3a over 8 sine alpha. These are the lambdas, right? So the angle of friction. Okay, children, this is my next example. A particle A of weight W resting on the rough horizontal floor is attached to one end of the light inextensible string wounded around a right circular cylinder of radius A and weight W that rests on the floor, touching it along a generator through the point B. The other end of the string is fastened to the cylinder. The vertical plane through the string is perpendicular to the axis and cylinder passes through the center of gravity of the cylinder and intersect the floor along AB as shown in the figure. The string is just taut and make angle alpha with AB. The floor is rough enough to prevent the cylinder from moving at B. A couple of moment G is called the cylinder, so the particle is limited in equilibrium. If mu is the coefficient of friction between the particle and the floor, show that the tension in the string is mu W over cos alpha plus mu sin alpha. By taking moment about B, find the value of G. We'll see how to simplify this kind of situation. So first of all, they have provided the diagram, right? It is easy for us. And you just need to continue the sum, right, including all forces and right. Okay, this is my particle P, right. It is attached by a elastic string and it's wounded by a cylinder, right. It's wounded, and also you just need to draw the complete diagram, right, including all forces and all. So these are my reactions and weight. This is tension T. This is also tension. This is the reaction between the surface and the particle. This is S, right. And this is my weight W of the particle. So again, this is capital W, the cylinder weight. Particle is simple W. So considering the equilibrium of particle P, horizontal forces is S. This is friction, right, of the particle. S plus T sin alpha equal W. Equation number 1. T cos alpha equal F dash, which is mu S. So the next thing is you have to simplify it using the simultaneous equations. Okay, considering the equilibrium of the particle P, so this is the result, right? I take two components to calculate the T value. And you know, the always the tension is trying to move the cylinder, right? To rotate it, but there is a moment around O, right, to the cylinder, so then it will be fixed. So this is A and B, right? A and B, and so I'm taking moment around B. So the reaction is and W are not useful, right? So that we just need to find the perpendicular of T, right? So how to find that perpendicular distance? So G into TD, right? So the perpendicular distance is D. So these are radius, right? I'm going to draw the. So these angles are same, no? Alpha by 2, alpha by 2. Actually, the P is the external position to the circle, right? So the AB and A, assume the up one is D, then AB and AD will be equal, no? Right. Considering the behavior of the congruent triangles. So these are alpha by 2, no? So we can find the AO distance, right? AO sine alpha by 2 equal A, no? Then AO equal A over sine alpha by 2. Alright, so AO. So the up one is so AB can be written AO cos alpha by 2, no? So AO is A over sine alpha by 2. So this is AB, A cot alpha by 2. So once we found AB mean, we can find the perpendicular distance BD. AB equal AD, right? Because these are tangents, no? Then AB equal the D equal AB sine alpha, right? So AB equal A cot alpha by 2 into sine alpha. This is D, right? So now we can take the moment around O without any fear, because now it's D also found. So we just need to calculate the G value, the moment value, right? So anyway the cylinder is equilibrium. So moment around B, GB equal, it's G minus TD, no? TD will be W mu over cos alpha plus mu sin alpha into D value. Say cot alpha by 2 sin alpha. So this is the final answer of the G. Okay, this is the end of the question number 3, right? Okay, children, so I put some homeworks to be done, right? So you can try this one as a homework. All right. And thank you very much for being with us, and I will catch you with the second friction lesson, right? If you have any doubt, please feel free to ask it. So you can comment in, right?